All right, today we're diving into digital signatures. You can think of them as the invisible ink of the internet. We're going to break down the theory behind them, and then the fun part, see how it all clicks together in a real Python script. Let's get to it.
You know, we talk a lot about encryption, right? About keeping messages secret. And that's super important. But what happens when the problem isn't what's in the message, but who really sent it? I mean, how can you be absolutely certain that email's from your bank and not from some fisher trying to scam you? Well, that's exactly the problem digital signatures were designed to solve.
And that question leads us right into the world of authentication. It's a different way of thinking. It's less like a locked box hiding a secret and more like an old-school unbreakable wax seal on a letter. That seal doesn't hide what's inside, but it proves without a doubt who sent it and that nobody has tampered with it on its journey to you. This really breaks it down perfectly. On one side, you've got encryption. Its whole goal is confidentiality, keeping things private. But on the other side, digital signatures are all about authentication, proving you are who you say you are. They also give us this powerful thing called non-repudiation. And all that really means is you can't sign something and then later deny you sent it. It's the digital equivalent of a legally binding signature.
So how do we actually create one of these unbreakable digital seals? Well, it all starts with a really clear blueprint. Before we even think about writing code, let's walk through this 4-step recipe that makes the whole system work.
Okay, so here's how it all comes together. First, we take the message and we create a totally unique fingerprint of it. That's called hashing. Then, and this is the genius part, you encrypt that fingerprint, and only the fingerprint, with your private key. That encrypted fingerprint is your digital signature. Now, when the receiver gets it, they use your public key to unlock the fingerprint. If the fingerprint they unlocked matches the fingerprint of the message they received, boom, they know it's from you and it hasn't been changed.
And this right here, this is a huge deal. It's so important for efficiency. We don't sign the entire message. I mean, imagine signing a 2-hour movie file. It would be incredibly slow. Instead, we just sign that tiny, unique hash. Think of it like this. You fingerprint a person, you don't take a full-body CAT scan. It's way faster, way more efficient, and every bit as secure.
So the theory is cool, right? But let's see how this actually works in the real world. We're going to take that 4-step blueprint we just talked about and turn it into a simple working Python script. This is where it gets really interesting.
But hold on. Before we write a single line of code, we have to talk about the absolute golden rule of cryptography. You can see it right here. We never, ever write our own crypto math from scratch. The math is just unbelievably complex, and the tiniest, most innocent-looking mistake can open up a massive, catastrophic security hole.
So why is this rule so important? Well, instead of trying to reinvent the wheel, and probably getting it wrong, we rely on battle-tested Python libraries. We're talking about things like hashlib for hashing, and cryptography for the signing part. These tools have been built, attacked, and perfected by experts for years. They're just way more secure than anything a single person could write on their own.
The best way to think about our Python script is to see it as a simple machine. It's a black box, really. You feed it a couple of specific inputs, it does its magic using those powerful libraries, and it gives you one predictable, secure output. That's it. Inputs in, output out. So, what do we need to feed into our signing machine? It's actually super simple. All it needs is the message you want to sign and your secret weapon, your private key.
And what does our machine spit out? Just one thing, a string of text we call a hex signature. That's it. That's our digital seal ready to be sent along with the original message.
Okay, so that's signing. What about the other side? Verifying. Well, that's another simple machine. This one takes 3 inputs. The original message, that signature we just made, and the sender's public key, which, remember, is available to everyone. And the output? It couldn't be simpler. It's either true or false, yes or no. The signature is either valid or it's not. There is absolutely no in-between.
And this is the moment of truth. On the left side, the receiver's computer creates a brand new fingerprint from the message it received. On the right side, it uses the public key to unlock the sender's original fingerprint from the signature. And then it asks one simple, critical question. Do they match? If they're identical, we get it true. We're good to go. But if even a single bit is different, it's false. Verification fails. This brings us to a really crucial concept in all of security engineering, and it's called failing safely. You see, a truly secure system isn't just one that works perfectly when everything is going right.
It's a system that stays secure and behaves predictably, even when things are going wrong.
This fire alarm analogy is just perfect. Think about it. You don't trust a fire alarm because it's quiet. You trust it because you know it's going to scream its head off the second it detects even a little bit of smoke. A good security script is the exact same. You have to be able to trust its warnings 100% when it tells you something is wrong.
So what does this actually look like for our script? It means there's no gray area. It can't guess or say, well, it's partially valid. No. If a signature is invalid, the script has to fail hard and immediately throw up a red flag. The default for any message should always be untrusted. A message only earns our trust after it passes that final mathematical check.
And look, this stuff is more important today than it has ever been. We're moving into an age of AI-generated content and deepfakes that will challenge our ability to trust what we see and hear online. In a world like that, the cold, hard, mathematical certainty of a digital signature, well, it might just be one of our last and best lines of defense in the fight for what's real.